Hi everyone, I'm Ron Klemenczyk with Magnus & Klemenczyk Associates here in downtown Seattle. Welcome to Rainier Square. Let's go inside and have a look at what makes this building so amazing. Rainier Square is the latest addition to the downtown Seattle skyline. Its tall, slender, and swooping form was only made possible through structural steel construction. Paying homage to its famous neighbor, Rainier Tower, designed by Minoru Yamasaki, this mixed-use urban development creates a whole new hub in downtown Seattle. Originally envisioned by its developer, Wright Runstead, to include residential apartments over 750,000 square feet of office space, over a podium that included a grocery store, fitness center, and other retail outlets, all situated above 7 levels of below-grade parking. Its complex nature demanded structural steel construction. Historically, buildings of this nature for the last 30 years have been built typically using a reinforced concrete core to brace the building for seismic and wind loads, surrounded by structural steel framing. This has proven to be a very economical and efficient way to build, yet you can see in this particular image the challenge, and that is the time lag required between the reinforced concrete construction and the structural steel. The challenge was to figure out a different way to build the building that would eliminate that time lag, thus speeding the construction of the building. Overall, the geometry was typical of most buildings. It had the low-rise core, a mid-rise core tapering with the form of the building, and then to the high-rise core at the very top of the building. That core in and of itself was not strong enough or stiff enough to brace the building for seismic and wind loads, so it needed to be supplemented by structural steel outrigger trusses and belt trusses. And those supplemental trusses provided adequate stiffness and strength for all the environmental loads. Once again, the interconnection between those steel trusses and a typical concrete core would have proved onerous. So the challenge was on to come up with a better way to design and build a building of this nature. The big idea was to implement a prefabricated modular structural steel system, including composite plate shear walls that were concrete filled, ultimately deemed SpeedCore. That SpeedCore was conceived or comprised of steel plates on either face of the concrete wall, interconnected by cross-tie rods at a spacing, in this case, of 12 inches on center. Those very robust panels were then stacked up like Lego blocks to form the core of the building. When Engineering News Record got wind of this new design and new idea of how to build the building, they wrote a story called Calculated Risks. The idea being, or the challenge being, no one had ever done this before at this scale, and all of the risks that might ensue in the coming construction. What wasn't known to the rest of the world at that time was that the design was about to be founded on 12 to 15 years of research that was started in the mid-2000s at Purdue University, here with Professor Krager and Professor Bowman in the Bowen Lab, where large-scale specimens had been under testing and investigation for years. Specimens that included unconcreted panels and concreted panels and all of their various connectivities. Ultimately, research expanded to the University of Buffalo, where Dr. Michel Bruneau and his team investigated more advanced geometries and more complex loading conditions. And then finally, Professor Varma and his team back at Purdue University investigated all sorts of details related to the cross ties of the walls, the connections of the walls, the fire response of the walls, and so on. So we proceeded with great confidence with more than a decade of research standing behind us as we move forward. In addition to the research, full-scale mock-ups were built. In this case, a mock-up investigating concrete placement and concrete mix design, so that we could proceed confidently that the composite plate shear wall panels would in fact be filled with concrete and provide the adequate strength and stiffness that we were demanding. In addition, a full-scale steel mock-up was done so that we could understand, the team could understand the fabrication process, the shipping and handling process, and ultimately the erection process. In this case, the erection team, who were charged with building the building, got to practice at full scale in a construction yard to understand how best to manipulate these very large panels in the field, including their connectivity, in this case, a welded joint from panel to panel. All of that homework went into the planning of this project before the structural steel arrived on site. Here you see the first trucks arriving on that fateful day when we started erection. The panels were lifted off the trucks and down into the hole, and then ultimately connected to the foundation. In this case, a very thick foundation mat slab was poured, receiving the stanchions that formed the start of the SpeedCore. From there, erection proceeded at a breakneck speed. Upwards of 4 floors per week were erected over the duration of the project, culminating ultimately 10 months later to the day. 10 months from the day that we started steel erection at the bottom of the excavation to the day that the final roof beam was lifted in place. 68 floors of construction completed in a miraculous 10 months. That's an incredible speed record compared to all buildings built in the last several decades. In addition to speed and the cost savings associated with that, countless truck trips in downtown Seattle traffic were avoided. A tremendous amount of embodied carbon was not included in this project because of the shortening of the schedule and the reduction of the construction activities. Rainier Square ultimately is now occupied and is a beautiful addition to the Seattle skyline. Let's go take a look in the Rainier Square lobby and see what the developer has left for us. We're here in the main lobby of Rainier Square, where the building's owner has put on display a portion of the core, SpeedCore, for all of the public to enjoy and see. In addition, the building's owner has put a commemorative plaque commemorating all of the hard work that went into building this most amazing building. Postscript to Rainier Square, there are numerous buildings around the country that are now implementing SpeedCore. 200 Park Avenue in San Jose, California, recently topped out its SpeedCore at a 20-story building, including use of the latest research on fire engineering related to the SpeedCore wall panels, where no spray-on fireproofing has been shown to be required. In Boston, construction is about to begin on another SpeedCore project, where bolted field splices will be used for the first time ever. Beyond those projects, other projects are planned in San Jose, California, and Oakland, California, to name just a few. You can see that SpeedCore truly was and is a game changer. Thank you for your time and for your consideration today.